Welcome to CET3136. This video is going to cover how we write a test bench in VHDL for a sequential design. And for this lecture, I am basically going to show you some code, and we're going to walk through the test bench and then the model sim simulation for this test bench. We're also going to attempt to break the test bench in several areas so that you can see how an error message or an error in the waveforms would be discovered. And hopefully you'll be able to use this lecture to supplement your lab where you will have to write your own test bench for your counters. You may want to implement test benches for future labs in order to ensure that your code is correct. So let's get started. On the screen, I have some code for a binary counter. And the first thing I'm going to do is walk through this code. I highly encourage you as we go through this video, take time to pause the video, type up the code yourself so that you can follow along in Quartus from home. And that way you'll be able to recreate the same outputs that I am creating here. So let's begin. I have my entity called binary counter at the top, and here are my inputs. I'm going to have a clock, a signal called up, and then reset bar, which is an active low reset. I'm going to have an output Q, which is standard logic vector 4 down to 0. So I have a 5-bit output for my counter. Within the architecture, I'm going to have a process where the clock signal is going to be the only signal we need to list within our process statement. And then below that, we have a variable called count_v. And this variable is going to hold the value of the counter. It's going to be unsigned because we're only counting positive values. And we're going to make sure that the size of this variable matches the size of our output Q. So this is really where we assign the number of bits the counter contains. We can change the size here and the size here in order to count up to a different number or to change the mod number of this counter. So after the variable, we have our begin statement, and we have an if statement. If falling edge of the clock, that tells me that the counter will respond to negative transitions. And then we have another if statement. If reset bar is 0. Notice that reset bar comes after the falling edge of the clock statement, which means that it is a synchronous reset. So if reset bar is low, then we will set the value of our variable count to be all zeros. Otherwise, if reset bar is not low, that means the counter should be counting. And then we have a case statement where we're going to count up or down dependent on the value of the signal up. When up is 1, we're going to count up, and that's accomplished with this piece of code right here, where we simply take our variable count_v and increment it by 1. If up is not 1, that means it has to be 0, and therefore we will count down or decrement count v as long as that value of up is not 1. And that's going to end our case statement. Notice that all of this is contained within the if statement that checks for the falling edge of the clock. So our counter is basically going to count or be reset on each falling edge of the clock, dependent on the values, of course, of reset bar as well as up. Once this loop has been completed, the value of count_v holds the value of the counter. We have to typecast that value into a standard logic vector value so that it can be stored into output Q. And this is the piece of code that we're going to be writing a test bench for today. And there's a couple of things we have to consider. First of all, with the size of this counter, it's a 5-bit counter. So you may be wondering, wow, do I have to test every single output case? Yes, you do, but we're going to be smart about it. We're going to take the advantage of loops so that you don't have to write an individual piece of code to check for every single unique output of this counter. Another thing that we have to consider is that we need to ensure that the counter counts up properly when the signal up is 1, and that it counts down properly when the signal down is 0. So these are some things that we have to consider. We're also going to have to implement the idea of a clock signal within our test bench, and we have to make sure that our test bench will appropriately reflect the fact that the counter should only count on a falling edge of the clock and that we should only reset if reset bar is low on a falling edge of the clock. So these are all things we're going to consider as we go through the code for our binary counter test bench. So in my next tab, I have the test bench for the binary counter. Beginning with the entity, of course, we're going to have an empty entity for any test bench that we write. And next, we're going to go to the architecture. At the beginning of the architecture, we're going to set up all of our stimulus signals. Those are the signals mapped to the input and if you have any in-out ports of your tested entity. So in this case, we have the input clock, the input up, and the input reset bar. So we're going to define those signals. Notice they're all standard logic with the clock having an initial value of 0. And then we have our observed signals, basically the signal that's going to be mapped to the output ports of our entity that we're testing, our UUT, unit under test. And so we have a signal Q to represent that. Notice the size here of Q matches the same size as our binary counter code. The next thing that we're going to define is a constant value called period. This is going to represent the period of the clock signal, and it's been selected to be 40 nanoseconds. The other variable that we're going to use, or not variable rather, but signal, is a signal called end_sim. Stands for end simulation. It's a Boolean value, so it's only ever going to have a value of true or false. And we're going to be using this Boolean value to determine when to end the test bench simulation. And we have to determine when the test bench will end because there's a clock involved, and I'll explain a little bit more about that later. So these are the signals that we're going to need to set up for our test bench. And once again, because we have a clock signal, we have to establish the period of that clock signal, and that's going to be 40 nanoseconds. So that's the time it takes to complete one full cycle. And then we're going to be using this Boolean variable called endSim to determine when the simulation for this test bench should end. Next, we're going to have our begin statement where we begin the architecture of our test bench. And you're going to have to map this test bench to the entity you actually want to test. In this case, the entity I actually want to test is my binary_counter.vhd file. So I've listed that here, and then I've mapped my stimulus signals to the signals in the port statement for that entity. Remember that this port map statement here is basically going to match or map the signals that you've defined here with the signals that were defined in your port statement for your UUT. Next, we're going to set up the clock. This happens right here. This is the piece of code that will establish our clock. Notice that it says clock gets not clock after period divided by 2 when endSim equals false, else 0. So let's sort of break this down, this piece of code down. So notice that the clock is going to get its the previous value of the clock inverted because of the not, and that's going to occur after half of the period we've already defined. So remember that with a clock signal, if the period is 40 nanoseconds, that means half of that time the clock should be high and half of that time the clock should be low. So we're establishing that fact with this piece of code right here. And what we're saying is that as long as this Boolean variable is false, we're going to continue creating this clock signal. The reason why we have to use the Boolean variable to control the clock signal is the fact that, remember, within VHDL, your code will continue running forever, and this code will run continuously, which means the clock will always generate new events. As long as you have this piece of code running in your simulation tool or on your bench, it's going to run forever. There's always an event that's going to happen because your clock signal is going to continuously be inverted after half of your period forever. So we're going to control the simulation with this Boolean value. As long as end simulation is false, we want to continue creating a clock signal. But at some point within this test bench, we're going to test all of the possible cases we can possibly test, and we don't need to continue running the code. When we get to that point, we're going to set endSim to be true, and that's going to stop the clock and force the clock to just be low. Once that clock has no more new events, none of your other outputs will have any new events, and the simulation will end. But without that, you'd go into Model Sim, you'd run your code, and it would literally run forever. And we don't need that. That's not very efficient. So that's why we have this statement here to control when the clock will eventually stop transitioning and just become a constant low. That's what this piece of code does. So that's the clock. The next thing we're going to initialize is the reset. So we're going to set reset bar to a value of 0. And then we're going to set reset bar to a value of 1 after 2 periods of the clock. So that should cause the counter to have an initial value of 0 once that reset occurs. So whenever we check our output in our waveform, we'll see that that is true. So now that we've set up the clock and the reset, we are now going to begin the simulation process. The first thing that we're going to do within our process is define a constant called n. It's an integer value, and it's going to represent the number of bits in the counter. In this case, we have a 5-bit counter, so n is 5. Next, we're going to begin our process. Oops, I'm going to take that out. We don't need that. Next, I'm going to begin our process with a wait statement. We're going to wait until reset bar is 1, which means we're not going to do anything else with this test bench until the reset has been complete. We don't want to start checking values while this piece of code is still executing. So the wait statement will cause the code to pause and make sure that the reset has been complete, which means in theory that the counter has been cleared out and has an initial value of 0 before we start checking to see if it counts properly. So we're going to wait until reset bar equals 1 or high, and then we're going to wait for an additional nanosecond. After that, we're going to set the initial value for up to be 1. That means we want the counter to begin counting up, and at this point, the counter should have a value of 0 because it's been reset up here. The next statement that you see is a wait statement, again, where we wait until the clock has a value of 0. Basically, again, we're getting to an initialization point before we actually start checking the value of the counter. We are waiting for the clock to become a 0, and then we're waiting for 1 nanosecond. Next, what we're going to do is use a for loop to check every single output of the counter as it counts up. Let's take a look first at the for statement. For I in 0 to 2 * n minus 1 loop. Let's break this down and make sure we understand everything in that piece of code. So first of all, I is an integer used within your for loop. It's like an index. It keeps track of how many times you've gone through the loop. And when you write a for loop, you have to define what you want I to start out at and what you want I to end at. So basically, when you say for I in 0 to 2 to the n minus 1, what you're declaring is how many times you want the loop to run. In this case, with our counter, it has 5 bits, and 5 is represented right here with our integer n. So we know, for example, that this describes the mod number. The mod number is 2 to the 5th. And we know that the range that the counter will actually count to will begin at 0 and go to 2 to the 5th minus 1. So we need to loop that many times and check every single output. That's what this piece of code is doing right here, where we say that I has to go from 0 to 2 to the n minus 1. Notice the * just represents the an exponential value. So * represents 2 to the power of n. So our for loop is set up so that we can check every value from 0 to 2 to the n minus 1, and we're going to loop continuously until we hit that point. Next, we have an assert statement. Take a very close look at the assert statement. We have assert q equals standard logic vector, parentheses 2 unsigned, parentheses I, comma n. What we're doing here is taking the value of I and comparing it to the output q. So for example, if I is 15, Q should be 15. If not, the counter is not counting properly and there's an error. However, we can't simply say assert Q equals I. We can't just put this, because I is defined as a constant. I is defined as an integer within your loop to keep track of the index of your loop, and Q is a standard logic vector. Those types do not match. We can't do that. So the first thing we have to do with I is typecast it from an integer value. This is a decimal number. This is the number 5. So we need to typecast that from a decimal value to an actual binary value, a string of bits that represents the number 5. And that's going to be accomplished where we typecast it right here. So we take the value of I, we say I need to typecast it to an unsigned value, an unsigned number. I need a binary value for this number, and it should be n bits long. That's directly related to the number of bits in your counter. So we're going to take the number I, typecast it so that it's no longer an integer. Now it is 2 unsigned. That's we're going to use 2 unsigned to create it as an unsigned value. And now it's going to be a binary value, a series of zeros and ones representing the number 5. But remember that 2 unsigned will create an unsigned number. We then have to typecast that so it's a standard logic vector type. So this is the double typecast where we take an integer value, convert it to an unsigned value, and then convert that to a standard logic vector value. That's how we will be able to compare the value of I to Q. So every time that I increments, I represents the value the counter should have. We're going to compare I to the actual output of the counter and make sure that it is counting correctly. So if it's not counting correctly, we're going to have a report statement where the report statement says count up of, and then we're basically going to typecast I again so that it can be displayed as an integer value on your screen. And that's how we create that. So if there is an error, this report will say count up of, and it'll tell you exactly what iteration of the loop you were on when it failed. Let's say that it counts up to 5 and then after that there's an issue. Well, it'll say count up of 5 failed, and you'll know that it failed when the loop was at the 5th iteration. After that, we'll have our severity where we label it as an error. And then we're going to wait for a clock transition. So we're going to wait until the clock is 0 again, wait an additional nanosecond, and end the loop. So this loop is going to set I to 0, compare I to Q as I counts up. As I counts up, in theory, Q should be counting up. And if there is no errors, this loop will run and we'll never actually see the report statement. But if the counter doesn't count up properly from 0 all the way up to 2 to the 5th minus 1, we will see an error here within this loop. So that's how we test that the counter is counting up. Next, we're going to test that the counter can count down. Keep in mind that this loop has run continuously until I gets to 2 to the n minus 1. So it's going to run until the value of the counter is 1, 1, 1, 1, 1. Then this loop will end. Then up will change from a 1 to a 0, which means now I should count down. And we're going to wait for an additional clock transition. We're going to wait for the transition where the clock goes from 1 to 0. So if the counter previously was at 1, 1, 1, 1, 1, and the clock makes another transition, that means the count has now rolled over back to 0 at this point. Then we're going to wait for 1 nanosecond and verify that the counter will count down correctly from 0. So you'll notice we have a second loop statement where most of the code from above is the same, except look at the for statement. The for statement has changed. For I in 2 to the n minus 1 down to 0. Because now that we're counting down, and we're counting down from 0, that means that the counter will begin counting from 0, 0, 0, 0, 0. If it counts down, the very next value would be 1, 1, 1, 1, 1, and then 1, 1, 1, 1, 0, and so forth. So when we start our loop, we need to evaluate that from that perspective. Now, that's just how this particular test bench was written. That's not the only perspective you could use to verify that the counter counts up or down. So if you're thinking that you have a different idea of how you would test it, you could very well be right, and I encourage you to explore that on your own as you prepare to write your test bench for Lab 7. Anyway, we have our for statement right here, where we're going to start at 2 to the n minus 1. We're going to go all the way down to 0. We're going to check the value of q for every value of I, and if those two do not match, we're going to get an error. Notice that the error message now says count down, so that I can tell the difference between an error and it counting up or an error and it counting down. If I took out the word down and I took out the word up, I'd have no idea where the error was. So by putting those in, I at least have an idea of whether or not it counts up properly and whether or not it counts down properly. From there, we have the same code where we have an error. The severity is labeled as error. Wait for the clock to make a transition. And then wait for an additional nanosecond before we check the next value of Q. Once we finish this loop, we have checked that the counter counts up. We've checked that the counter counts down. There really isn't anything else to check. We've checked the reset. So at this point, it's time to end the simulation. When you put this piece of code here, that NSIM is true, now we're signaling the clock signal up here to become stagnant. Up until this point, your clock is continuously going from 0 to 1, 0 to 1, 0 to 1, as the rest of your test bench executes. Remember, VHDL runs everything concurrently. So once we're done simulating, we no longer need our clock signal to continue producing an event. And so by having this piece of code at the very end, NSIM equals true, our clock signal is now going to become a stagnant low because this piece won't execute if NSIM is true. It'll only execute if NSIM is false. So that's how we end our simulation. So after we've checked all of our cases, we've checked the reset, we've checked whether it counts up, we've checked whether it counts down, we're going to set NSIM to true so that we can end the simulation. There's a wait statement, and then that's basically the end of our architecture. So this is the test bench that we have to verify whether or not our binary counter works the way we intended it to. So the next thing that I'm going to do is open up ModelSim and do some simulations with the test bench code. So I already have a new project within ModelSim, and I have my files already loaded. I'm going to go ahead and recompile them. Okay, both of my compiles were successful, and I'm going to start a new simulation. I'm going to add my waveform. All right, so I've got my signals, clock, up, reset bar, and Q added to my waveform. I'm going to go ahead and go to simulate, run all. The first thing I want you to notice is the absence of error messages as we run that code. There are no error messages, so we can most likely assume that everything worked okay. But let's take a look at the waveform as well. So here's our waveform. We can see that this signal right here is our up. So up is initially 0, and then it becomes 1 right here. Here's our clock signal with a period of 40 nanoseconds. Here is our reset bar, where it begins with a value of 0 and eventually becomes 1. At this point here, the counter should count up or down, depending on the value of up, on every negative transition. And then we can see the output Q right here. So we can see that when the reset bar is activated, the output is low. Then once reset bar goes high, we notice it goes from 0, 0, 0, 0, 0 to 1, 1, 1, 1, 1. If that's off-putting to you or you're wondering why, just look at the waveforms. Reset bar goes high right here. There's a negative transition right here, and it may be hard to see, but right here, up has a value of 0. Up has not been initialized to 1 yet. So on this negative transition, it's actually being signaled to count down. That's why you see it go from 0, 0, 0, 0, 0 to 1, 1, 1, 1, 1. And at this point in our code, we haven't started checking that it counts up yet. At this point in our code, we're really only, if we go right back to our code, we're really only at this point where reset bar has gone from 0 to 1 after 2 periods. And then we have to wait until reset bar is 1 and then wait for a nanosecond. So in that split second of time, because your reset bar has been set from 0 to 1 and your up is going from 0 to 1 in that small period of time, we actually see it count down 1 time before it begins counting up right here. And we can see that the count goes up. And you can scroll through the waveform and you'll be able to see that it counts up the way that it should. We can also continue to scroll and look for our value of up to go from 1 to 0, which means at this point I should be counting down. And we talked about in the code how once up goes from 1 to 0, you're going to have a value in the counter of 0, 0, 0, 0, 0, and then from this point it's going to count down. Once again, if you look closely at the waveform, you'll see that the negative transition occurs right here while the counter is still being controlled by up being 1. So we go from 1, 1, 1, 1, 1 to 0, 0, 0, 0, 0. Right after this negative transition, up transitions from a 1 to a 0. So on the next transition, which is right here, we start counting down. And then it'll count down all the way back down to 0. And then the simulation will end at that point. So there's our waveform showing how the test bench is working currently. Now what we're going to do is throw some errors into our code and look at how the test bench will respond. So I'm going to go back to the binary counter code. And the first thing that I'm going to do is change the reset value. So instead of resetting it to 0, which is what is expected, let's make count V something else. Just at random, I'm going to pick the value 0, 1, 1, 1, 0. I'm going to save that code. Go back to the test bench. Recompile the binary counter VHD file, because that's the only one we changed. We didn't change the actual test bench code, so you don't have to recompile that. And we're going to start a simulation with our new code. And I'm going to add my signals, simulate and run. Now you'll notice all these error messages. And with each error message, you'll also be able to see exactly what iteration of the loop that error occurred. So count up of 0 failed, up of 1 failed, up of 2 failed. This counter basically failed for every possible output value on the way up, as well as on the way down. See, it gets all the way up to 31, it failed every single time, and then it fails counting down as well. And obviously it's going to fail because we affected the code, but let's take a look at the waveform as well and verify that these error messages match what we expect. So here's our wave. So here's our signals. we can see that reset bar is low. And because it is a synchronous reset, the first negative transition is where that reset is going to take place. And so we see the reset occur. This is our reset 0, 1, 1, 1, 0, which we said would be the reset point if you go back to the code. This right here is sort of a default value because nothing has been assigned to the output of the counter at this point. So right here on our first negative transition, we have the synchronous reset where the reset point has been changed from all zeros to the value 0, 1, 1, 1, 0. After that, you can see right here at the next negative transition, reset bar has gone high, up is still low, and it starts to count down. After that transition, on the very next transition, we see that up is high, so now it's going to start counting up, but it's going to start counting up from this value. This point right here should be an output of 0, 0, 0, 0, 0 per our test bench. So it's really important to understand how you wrote your test bench and what you expect it to do. Because if you don't understand how you wrote your test bench, then you won't necessarily know if your test bench is working as intended. Again, if I go back to the code that we wrote, this code was written with the intent that the very first time I get into this for loop, the count should be 0. So if that's the intent, then yes, we have an error. Just make sure you know that intent as you're looking at your test bench or as you're writing a test bench so that when you test it, you know exactly what to expect. Ultimately, your brain should be the end all on how a test bench should work. You should know the test bench in and out. Make sure you know exactly what should come out of your test bench. So that's why we see it start at 0, 0, 0, 0. It goes to 0, 1, 1, 1, 0 because that's the reset point we defined. And then it begins to count down, and then it begins to count up right here, and it does not have the right values. So you're going to see an error for basically every output state of this counter because it doesn't match what the test bench was expecting, which is for it to start at 0 and count up sequentially to 31. So I'm going to go back to the code. I'm going to take this out and put that back. Next, I'm going to mess with the case statement. So instead of counting up when this value is 1, I'm going to make it a 0 and do another simulation. So I'll go ahead and recompile. So I have a new simulation. I'm going to go ahead and add my signals to the waveform and simulate. And once again, I can see some error messages. And we can see that basically it failed counting up as well as counting down. And if you look at the waveform, you can also see that. So we can see again, the reset is working as intended on the first negative transition. We have that synchronous reset. Because up is still low at this negative transition, it counts down 1 time, and then up goes high. We have our next negative transition, and then it begins to count down instead of counting up. Now you have to ask yourself, is this really an issue? Is this really wrong? It is counting down properly, but it doesn't count down when up is a 1. It counts down when up is a 0. That's what it's supposed to do. But we changed that. So at the end of the day, whether or not something is wrong sometimes goes back to the specifications. This counter counts fine. It counts up and it counts down. But it's supposed to count up when this is 1, not 0. And if that's your specification, then that means your product doesn't work as it's designed. And that's an issue. So That's another way that we can check that the counter works as designed. This could be a simple error. Putting a 0 instead of 1, that's an easy error to make. So a test bench, if written properly, is a great way to catch an error like this. And remember with test benches, the person writing the test bench is almost never the person who wrote the code. So you have two different minds looking at this problem from different angles and different perspectives. And that's usually how a test bench is very successful, is because the person writing the code is not the person who's testing it. So the person writing the code may just be blind to something because they're in it. They're the one writing every single line. Whereas the person testing it has more of an outside view, and they're able to see things that the person who actually wrote the code cannot. So for our last quick example with test benches, I'm going to change this back to 1 so that it counts up the way it should, but then I'm going to cause it to count up by 2s instead of counting up by 1s. And again, we'll see an error. Actually, I'm going to make it count down by 2s. So again, we'll see an error. So I'm going to save that and do one final simulation. So here's our simulation. Let's look at our output. Once again, we can see it failed. It didn't count the way it should have. Here's our waveforms. And we can see that the counter was initialized to 0. Before the up signal goes from 0 to 1, that means, again, it's still counting down right here because the negative transition comes before that one. So it's counting down, and it counts down from 0 to 1, 1, 1, 1, 0. So when this signal goes from 0 to 1, on the next transition, it goes up to 1, 1, 1, 1, 1, and it doesn't start at 0 now. It doesn't start counting up from 0. It starts counting up from 1, 1, 1, 1, 1. So once again, we have an error. So this is how we're going to approach writing a test bench for a sequential logic, something that has a clock signal, something that we need to really take advantage of looping because we have a lot of conditions to test. And I encourage you to type up this example on your own, and I also encourage you to determine a pitfall in this test bench example. I'll give you a hint. If I go back to the code, I'm going to put this back to normal. If I change this to 1 so that when reset bar goes low, the counter doesn't get the value 0, 0, 0, 0, 0, it gets the value 1, 1, 1, 1, 1. So I'm going to change it so it doesn't truly reset to 0. And if I go back to my model sim, compile that, I'm going to start a new simulation.